Laura.
Well, thank you very much, Rick, and thank you all for coming. It's my pleasure to welcome you on behalf of Roger Wakimoto, who is our director. Roger is in Nanjing, giving a series of lectures. There's over 200 students from the region who are there to hear about extreme weather events. And so he sends his regrets, and he sent me to pinch hit for you, for him, rather. So I understand that some of you are new to this meeting and new to NCAR, and so Rick asked me to take a few minutes to talk about our organization and our history. So we are a federally funded research and development center sponsored by the National Science Foundation, and our mission is really threefold. We want to understand the atmosphere, the air around us, and the physical, biological, and social systems that affect it. So you can imagine that there's a symbiotic relationship between your mission and our mission because, of course, hydrological systems are extremely important to the atmosphere. The other thing that we want to do is we want to serve, extend, and enhance the capabilities of our community. And our community is the university community that we serve, as well as the broader scientific community. So that would be you folks as well. And finally, we want to foster the transfer of knowledge that we learn here for the betterment of life on Earth. So that's our tech transfer component of our mission. We started back in the late 1950s when 14 universities got together and formed what is called the University Corporation for Atmospheric Research, UCAR. And they went to the National Science Foundation and said, you know, there are really big problems in the atmospheric sciences that we as individual departments are not able to solve on our own. So we really need a center that is going to be able to synthesize our efforts and extend our efforts. And that was the formation of NCAR. The beautiful building that I guess you're going to visit tonight for your banquet was actually constructed in the early 1960s. The construction finished in 1966, and that building is actually owned by the National Science Foundation. It was designed by I.M. Pei. You'll have lots of time to explore the building, I hope, and the beautiful exhibits that we have up there. Finally, today, UCAR is a consortium of more than 100 universities and almost 50 international affiliates. And we have a brand new president who was just appointed by the board in January of 2012. His name is Tom Bogdan, and he also is not able to be with us today, but he sends his good greetings, good tidings. So the last thing that I'd like to say is that you know, we at NCAR really want to congratulate you and celebrate all of the research that you do about processes, because they really are important to our Earth system modeling efforts here. We have several community models. You may have heard of our climate model, but the one that's probably most relevant to you is our research, our weather and research forecast model, so-called WRF model, and in particular WRF Hydro. And the development of WRF Hydro is led by Dave Gotchis. I understand that Martin Clark, another member of our staff, will be giving a talk on WRF Hydro later in the week. So you will see how your research results are really impacting us. And so we're very grateful for that, and we thank you very much. That's all I wanted to say, except to welcome you to NCAR and best wishes for a very successful meeting.
Great. Well, we can get the program going. Jim, do you want to, so you don't need to come up here? You can take over.
Thank you very much for that kind welcome. I just have a couple of comments on the program today. Rick has already given you some details. Just a reminder, in reverse chronological order, even if you don't go to the banquet, you are encouraged to come to the film showing that is at, I believe, 8 o'clock after the banquet. And there's the banquet, and as Rick mentioned, the afternoon is relatively free, or there are a couple of workshops that you are encouraged to attend if you are so inclined. This morning's sessions, which begin at 10 o'clock, will be like yesterday in this room and that room. The experimental watersheds sessions will be here. The modeling sessions will be over there. The experimental watersheds ones is a continuation of the sessions that started yesterday. This morning, we have another one of our plenary speakers where we have invited luminaries in the field to give some addresses. The Wolman lecture is this morning. The Wolman lecture was initiated in the first biennial. This is the third one. Meant to honor the contributions of Reds Wolman, who until his passing in 2010 was a professor at Johns Hopkins University, where he had a career of over 50 years at Johns Hopkins, and in that time he made significant contributions in a wide range of disciplines spanning hydrology, geomorphology, and sanitary engineering. He was actually the founding the professor of the sanitary engineering department, which in that branch of his work led to more of like humans in the water system, which is the subtitle of the Wolman lecture series, which actually I didn't know until our invited speaker pointed it out. He said, I thought, which I'll introduce him, I thought it was about geomorphology in water. I was like, well, it is. It says it's about humans in water. Well, that just indicates the breadth of Red's work. And in that broad range, he just left a tremendous legacy of scientific knowledge. And fortunately, in addition to that knowledge, he left a vast legacy of people who have been trained by him and are still among us, leading the charge in a wide range of disciplines. And our speaker today, Dr. Tom Dunne, is among that crowd and perhaps represents the energy and the work and the spirit of Reds Wolman, perhaps better than anyone, and it's an honor to have Dr. Dunne speak to us today. Tom is a professor of environmental science and management at the University of California, Santa Barbara in the Brin School. Prior to that, he was a professor at the University of Washington. Prior to that, he was at McGill. Let's see if I get it all right. Prior to that, he was at the University of Nairobi, where he told me this morning, teaching hydrology in Africa. There's no textbooks, no access to textbooks, so he wrote one as a young man, which has become a standard textbook, and in my opinion, a benchmark. If you're going to write a textbook on water and geomorphology and hydrology, if it doesn't match water and environmental planning, start over. Before that, he did his PhD with Reds Wolman at Johns Hopkins, and in that time as a young man, he produced a suite of papers that, like the book, has been a benchmark of excellence, perhaps one of the first hydrologists to walk around in the rain and say, well, that's the model, the process we were taught, that's not how it actually works. I don't see water flowing over land. And as a result of that, he actually has a runoff generation mechanism named after him, Dunne overland flow. What greater honor can hydrologists have? And so his career has spanned, in addition to the contributions to hydrology, actually much of his career has focused on geomorphology and the mechanics of rivers, and I believe that's what Tom is going to talk to us about today. The title of his talk is, I will know as soon as I open the file. This should be open. Okay, I'll close this one. Where's it at? Down here. There we go. Tom is going to talk to us on the evolution of floodplain complexity. And I will leave it at
Thanks, Jim, and thanks for the invitation to come. And I thought I would talk about fluvial geomorphology as part of Reds' contribution because I don't know how many people know this, but his original research career, his first 15 years or so of his work, both at Johns Hopkins and before that for the Geological Survey, Reds was studying rivers and floodplains in the field, in the lab, but always with a sensitivity towards the significance of his work for society. And he sort of seamlessly connected those two issues, doing experimental science and the significance for society. He telegraphed that continuously throughout his mentoring career, even before he got into these larger issues of water availability and water quality that the first two Wolman lectures have talked to you about in the last two Wolman lectures. So I chose this topic, the evolution of floodplain complexity. But before I do this, I want to make what I call the graduate advisor's disclaimer, because you all, those of you who are in the upper half of the age distribution here, who've been advisors for a long time, know that behind every speaker there's a number of graduate students or postdocs. And like I often say, the rule is if I say I did something, it means they did 90% of the work. If I say we did something, it means they did all of the work. Okay? So just to remind me, these are the last four of my fluvial geomorphology graduates, I mean the most recent of them. They're all out doing their own things now. But their voices are rattling around in the back of my head, and sometimes you'll see a reference to papers which they have senior authored and so on. So, for those of you who don't think of floodplains in terms of their geomorphology, in other words, how they originate, how they're formed, how they're maintained, and so on, I'll just emphasize that I'm using a very loose definition of floodplains as just the areas that are flooded in a range of frequencies. I'm not sticking with the, what sort of became known as the Leopold and Wolman floodplain that's just inundated in the current flood regime by the 1.5 or 2 year flood. It's not that narrow a definition. There's a broader range of floods that inundate large areas of valley floors, and they construct these plains and continually modify them. And the important thing about that modification is that the floodplain is that part of the terrain that's created by the river with sediment that's intermittently transported. Okay? Now, most of the rivers that we get to study in North America and Europe have been tamed and their floodplains simplified through drainage and embankment building and so on, and filling of the topography of the floodplain. And so we don't get to see much, in the well-studied cases, don't get to see much of the true complexity of a floodplain that would be created by a river if we left it alone. So these are areas in Latin America that have not yet been tamed or filled, and they just remind us that left to its own devices, the river creates a lot of very subtle topography. Amplitude of the topography of the floodplain is roughly, I suppose, the depth of a river. But nevertheless, this complex topography has a tremendous amount of significance for human affairs, whether they're this one, which came to the fore in 2011, and within a year or so, it had been featured in the most recent National Research Council committee report on flooding, because when the Chao Phraya flooded in Bangkok and upstream of Bangkok in 2011, it's no longer some people in a developing country being flooded out, which doesn't typically make the greatest international news anymore, but it's the fact that that floodplain has, within the last decade, become so intensively developed, and is now the site of a lot of the world's manufacturing capability for electronics and things, that this flood disrupted supply chains all around the world in the same way that the Japanese earthquake did. So all of a sudden, we're reminded that there are a lot of large, newly developed floodplains, newly developed in the sense of human developments, where we don't have strong engineering control on the river or simplification of the floodplain. There were some dikes in Bangkok, but they failed. But as a result, these areas are flooded frequently. And I want to, again, in sort of the sense that if Rez were here, he would be saying, yeah, okay, so the big picture is, from afar, is there's a lot of water around in complex forms and so on, and the topography got flooded in a very complex way. But don't forget that the impact is all the way down to the lady hanging onto the street post in neck-deep water. It's humans on all those scales of society. Now, if you also look at earlier but very recent floods in the Chao Phraya, we notice in each of these cases it had a different peak discharge, but the inundated area varies significantly and in a very intricate way. So the topography of the floodplain is controlling not the peak discharge of the flood, of course, that's a watershed problem like we heard a lot about yesterday, but the inundation pattern. How does a discharge of a certain magnitude and duration invade a floodplain and inundate places where the topography was so subtle that the society didn't particularly notice the topography and didn't therefore realize the enhanced risk in certain zones. So there's a good deal of concern these days about the major, particularly tropical and subtropical floodplains. Not only are they close to sea level, but sitting at the bottom of large watersheds with very intense hydrometeorological regimes, but they're also increasingly being developed in ways that are not particularly resilient to being flooded. Okay? Another one that's very recent that made the news was the CUAHSI, where it's long been known this was a river that has gradually shifted its course and its floodplain over hundreds of kilometers towards the west, and then in the summer of 2008, suddenly burst its banks at the upper end there. By the way, let me see if I can, it burst its banks over here, and as the news media and NASA put it, it abandoned this channel more than 200 years ago. The flood swept down through India and China to join the Ganges River, which is right here, and swept over a region not accustomed to flooding and put 1 million people out of their homes. So again, I have a sense that there's a need to improve our ability to predict inundation patterns in these floodplains, and that prediction and recognition of the hazard and recognition of how the channel may continue to evolve is best done through studying how the floodplain was formed in the first place by the river. Now, in this country, as I said earlier, we've got most of our rivers under control most of the time, but a major new interest in floodplain complexity and river channel migration and the continuing interaction between them is, of course, we're spending a lot of money now on river restoration for ecosystem reasons and so on. And so we're doing things like taking a river that was simplified and trying to put some natural complexity and natural mobility back into the river, reconnecting former meanders by things like this. And then, of course, the question is, so what happens next? Which is not usually a question that's asked in a river restoration project, because we're still back in the idea that you control these systems. Right? Now, you're going to put them in a new position like this, and they'll still be under control. But of course, when you add this complexity and mobility, the river typically wants to start doing something else. And it would be nice if we could predict those. And we have a serious new interest in reconnecting channels with their floodplains to take advantage of the potential for floodplain inundation, to develop a complex series of environments from places over here that are close to the channel and therefore have an inundation regime and a water chemistry and an ecology that's closely related to that of the main channel. And then as you get hydraulically further and further away from the channel, then there's a complex but recognizable trend in the water chemistry because of the difference in exchange rates between channel and floodplain. And so there's the potential to harvest a great deal of the complication that this floodplain formation builds into the landscape because it creates some of the complexity that ecologists are trying to reintroduce into the river. Of course, we are increasingly getting to take these larger rivers seriously and completely re-engineering. This is the Kissimmee. These are chutes on the Missouri River that the Corps of Engineers has been told to clean out, to connect the remaining river with off-channel habitat to save the pallid sturgeon and so on. So this is being done under the direction of the Endangered Species Act. Oops. And again, the question arises, well, what happens next? You know, what happens to that water body once you've cleaned it out again? So, as I often say when I'm talking about this topic, the fact that I'm saying things that can be really complex doesn't mean, if we're doing research on how that complexity arose, we want to get postmodern about it. We have to organize our thinking into some kind of a research agenda. So you look at a range of these cases where the channel and the floodplains evolve. We can identify three sorts of processes. Now, of course, if we all talked about it for long enough, we could probably identify more, but three that really stand out to me is that channel bends grow, and in doing so, they produce lakes eventually in the floodplain. So you've got an in-channel set of processes. Second option is that new channels and new lakes can be formed on the surface of the floodplain, not by the main channel itself migrating. New channel formation. And then the next thing that can happen is if you build lakes in there, depressions in the floodplain, whether nature does it or the Corps of Engineers does it, it's a sink for sediment, fixation of organic sediments, et cetera, et cetera. So these lakes, on some time scale, are going to fill up. And as they fill up, again, they go through a series, a sequence of hydraulic conditions, water exchange with the main channel, therefore water chemistry, and eventually a series of invasions by the biota. So it sets the filling sets in train a whole set of ecological processes. Go from water-rich to land-rich, if you like. Okay, now, as geomorphologists, our basic goal is to do this, to understand and predict the behaviors of landforms. Right? And what we try to do in our explanations is employ fluid mechanical theories when they've typically been tested in labs. Right? Now, what we would like to do, although this is, if you like a fairly early stage, I would claim, in the agenda building, we'd like to express these theories at field scale with realistic hydroclimatology, realistic sediment supplies, and tectonic constraints. Now, I'm pointing this out even though I'm not going to talk about it in this talk, except to say that particularly in the Amazon, we have tried to do some work on defining how these three sets of boundary conditions, if you like, act. So you have to predict watershed scale, i.e. whole Amazon basin scale runoff, and then the hydraulics of that runoff as it goes over bank and so on. We've done some work on that. How much sediment various tributaries of the Amazon or other watershed or other rivers are bringing to the table to build the floodplain at some particular valley location. And also, again, in the case of some of these very large lowland rivers, very subtle tectonic processes that bend the crust or fault the crust affect what the river's doing. So, like I say, I'm not going to talk about this in this talk, but it's in the background. Now, I initially, just for the sake of hopefully some clarity, I'm going to reverse the order that I initially introduced these three research agenda items, if you like, and talk about number 2 first, number 3, and so on. And I'll end with 1. Now I want to again, try to break through the complexity by having you imagine a scale of what I call floodplain erodibility, right? And make the distinction between what I'm calling erodible floodplain surfaces and non-erodible floodplain surfaces. So if you're in the middle of the Amazon River basin, the floodplain, this is the Purus River, has about a drainage area of 350,000 square kilometers, so it's a decent-sized river. It has a very low gradient, 5 times 10 to the minus 5, or 5 centimeters per kilometer. When the water goes over bank into the floodplain, that water is first of all flowing on a very gentle slope through a dense forest canopy with clay-rich, cohesive alluvium. The chances of that flow being erosive, being competent to erode a new channel, is very low. So all the action, all of the modification of the channel, and therefore the extent to which the floodplain is modified by the channel and by overbank flow, they all got to take place inside the channel. Because once the water gets overbank, it can't erode anything. Okay. Now on the other, not quite extreme, but if we go to the Sacramento River, north of Sacramento City, the gradient's about 10 times higher, gradient of the floodplain. The forest is thin, and the alluvium is sandy, non-cohesive. So in this case, when the water goes over bank, in some part, it goes over the floodplain, in some places, that we'll get to in more detail in a minute, in some places it is competent to erode a new channel on the floodplain. So what that does is it short-circuits the process of increasing the bend growth to get this very sinuous channel, and it allows the flow to build new channels on the floodplain and to short-circuit the bend that the river was originally flowing in. The result then is that we, in this case, the non-erodible floodplain, and of course, most other large rivers in the world are somewhere between my two extremes, right? So I think that should be pretty clear. But if we have no incision in the floodplain, channel growth is limited to in-channel processes, and the river eventually develops an adequate or large enough sinuosity so that eventually one bend erodes its way into another bend, and the boundary between them, the barrier between them collapses, and the river flows through it in the form we call a neck cutoff. In this other case of the erodible floodplain, bends will grow, but before they've grown to this degree of sinuosity, an event comes along that produces a deep enough, fast enough overbank flow to erode a new channel and cut that bend off and straighten itself, and then leaving behind an abandoned channel, which is a lake in the floodplain there, but again, gradually redeveloping new bends in the main channel, and the whole process sets off again. So where we can incise new channels, the cutoff process, or bend short-circuiting process, if you like, we call a chute cutoff. So erodible floodplains, non-erodible floodplains, chute cutoffs, neck cutoff, result in differences in sinuosity and lots of other characteristics I'll be talking about in a minute. So then, with that background in mind, we take a look first of all about the condition where the channel can, the overbank flow can erode new channels in the floodplain. Now, this is the thing that happens basically most commonly as water goes overbank on these erodible floodplains. This is the 1993 flood in the Missouri River. And after the 1993 flood, you see that at a certain place, the river went overbank, started to cut a new channel. This is the chute, right? And eventually, it exploited that in a number of other floods and eventually cut its way through to start short-circuiting this channel and leave what would have been an abandoned channel behind. As you can see, there's some telltale straight lines in there. The Corps of Engineers have now got back in there, and they're trying to control this and make sure that the new chute stays open because it creates off-channel habitat. But nevertheless, that's basically the process. Now, Jose Constantine, in his PhD thesis, made a complete survey of the record of cutoffs in the Sacramento River, in about 160 kilometers of the Sacramento River, looking at old maps and old air photographs. And basically, on the air photograph record, going back to 1938, he was able to identify 10 chute cutoff events, which are outlined in white here. And unfortunately, because the colors are gray and light gray, it's not so clear to see this, but basically, it's probably best seen in this picture here. You see that there's this opening of a wedge of erosion into the floodplain that initiates the process, and then this bend was eventually cut by this chute along this path indicated by the white line. So what we tried to do was we basically discovered then that these new chutes get formed at a certain place in the bend where the curvature has put the high velocity water closest to the bank, on the outer bank, and the super elevation is highest there, and there's the greatest probability that water will go over bank right in that location. And that's the place where most of these chute cutoffs originate. So we took a channel and floodplain DEM of just a piece of the Sacramento floodplain, just for illustration. And Jose ran a two-dimensional flow model and predicted, in this case, these are the flow velocities mapped in these continuous colors that I always have trouble making much sense of. But the pattern I want to try to show you is that right there on the downstream side of the bend, and right here's another, the red, the warmer the color, the higher the velocity. So those are the locations in this overbank discharge. That's about 2.5 times the bankful discharge of the, no, let's call it 3 times the bankful discharge, just to give you a scale. Anyway, that location, just downstream of the, if you just add up the curvature all the way around a bend from the crossing, then right where that total curvature maximizes is where the water goes over bank at its fastest velocity and starts to cut these new channels that he recognized on air photographs. So we then constructed a simple one-dimensional model of that process. So here's, if you like, this is the picture. The water's going to go over bank here and head across the floodplain to the other part of the channel. So here's a one-dimensional model of that water, which has a certain depth initially, right, set by the flood stage. And it's going to flow down here over a vegetated floodplain surface. Vegetated floodplain surface has a gradient of the floodplain, so that goes into the calculation as well. The role of the vegetation is represented by a set of cylinders with a spacing and a plant diameter, stem diameter, if you like. So all the results were calculated with different combinations of the ratio of spacing to plant stem diameter, using a hydraulic model that Jim Smith of the Geological Survey had developed for floodplains in the Northern Rockies. Anyway, what we do, and I'm not going to drag all through this whole calculation, just point to the nature of the results. If you want any more details of it, the reference is down here. But the idea is the water goes over bank with a certain depth and a certain slope. It encounters the vegetation. The drag of the vegetation extracts momentum from the flow. You can calculate that momentum extraction using Jim Smith's model. And then the question is, how much excess momentum is retained by the flow, and can that excess momentum exert a high enough shear stress on the floodplain surface in order to erode it. Right? Now, in other words, the shear stress that has to be overcome is a characteristic of the valley floor alluvium, or the floodplain alluvium. So that's the simple scheme. Now, again, without going through the details of the results here, the summary diagram basically says, well, if you have let's go to the Amazon. If you have an Amazon-like low gradient, high density, cohesive alluvium and high density vegetation, the chances of you exceeding the threshold of incision, the threshold shear stress required for incision as the depth of flow in the channel and the floodplain increases is very low, because you would need to have an extremely sparse vegetation at such low gradients for the floodplain surface to become erodible. And of course, in the middle of the Amazon, you don't have sparse vegetation covers, and so that's why you don't incise the floodplain. Whereas if you're in the Sacramento with the steeper gradient and the sandier alluvium and so on, you can incise the channel with a denser floodplain vegetation. And let me say another thing that comes out of these calculations, by the way, is that the vegetation that we're talking about that's effective at extracting momentum and preserving the floodplain against incision is not the big trees that have a large diameter, would give you a lot of drag, but they're spread far apart because of the canopy that they need. So the momentum extracting vegetation is the fine scale, brushy kinds of vegetation with many stems and high density. Okay? So that's what so that's our basic first order, if you like, explanation of the difference between these two kinds of environments. And we have a simple one-dimensional hydraulic and erosion model that allows you to try to separate out the controls of gradient and depth, therefore discharge magnitude, vegetation on the floodplain, and so on. Now, if we then look at, well, of course, and so it's the explanation is, therefore, why chute cutoffs short-circuit the bend growth process on these conditions and don't here. And if the bends are not being short-circuited relatively frequently, the river will continue its migration, its in-channel bend-growing processes and develop these neck cutoffs. And a consequence of that difference is that typically the diversion angles, that is, what's the angle that's left over when the channel here short circuits through collapsing this barrier, then the difference between the original orientation of the flow and the orientation of the upstream and downstream arms of the resulting lake make a big difference to how the abandoned lake fills up with sediment. You notice in the Purus here, there are a lot of oxbow lakes in the floodplain that don't fill up. They stay open for a very long time. Right? There's one on the Amazon, the main stem of the Amazon, that seems to be at least 5,000 years old, for example, and no signs of even approximately filling up. Okay? So if we take that connection between my number 2 issue and my number 3 issue, these are the diversion angles. So in this case, and by the way, these are both cases on the Sacramento. So we're talking about the same flows and the same sediment loads and so on, same gradients. But this one, improbably, at least in the modern era, developed by a neck cutoff. And therefore, the angle between the original channel, and well, now the continuation of the channel, and the Oxbow Lake, in this case, is very large. Right? Whereas in this case, the river has formed chute cutoffs twice in 18 years, and each time the diversion angle went from this to this, and then that to that. It was a few tens of degrees, whereas these are much larger. Now, so that's the first observation, that the form of the cutoff affects the diversion angle between the channel and the abandoned lake. Next thing we observe is that the lakes that have a high diversion angle tend to stay open, as open water, for a long time. This one hasn't filled up in 134 years. It's filled up the mouths of the arms, but not here. Whereas, in this case, the river has formed two chute cutoffs, two lakes, and filled up both of them in 18 years. Right? But it has a much lower diversion angle. So we tried to address the conditions that cause that difference by making velocity calculations with a two-dimensional flow model for a sort of simplified expression of that diversion angle here. So here's the original channel. It was cut off by a chute cutoff. Here's the new orientation, and this abandoning channel, if you like. The channel is still connected to the main channel. There's water going into that abandoned channel. And what we calculate is should happen in a case like that is that as the water goes around this new, the old bend, not the new bend, a separation zone of low velocity and recirculating flow will form on the inside bend. Well, that then doesn't contribute to the conveyance capacity of this abandoned channel. So the flow that's going into the abandoned channel is much narrower than the abandoned channel itself. So if we call the width of that conveyance capacity for water going into the bend mu, and what we find is that mu, the percentage width here, mu, diminishes very strongly as the diversion angle increases. Okay, so that is a two-dimensional flow model prediction. Okay, now then what we did for this paper is we then took the simplified, the reduced discharge that can go through here, calculated what that discharge will be, and then put that discharge across the whole channel downstream of the separation zone and calculated not only its discharge, but its velocity and its sediment transporting capacity and so on. Now, what we've done since is model with the two-dimensional flow model, not only the flow, but the sediment entering here. And of course, the sediment deposits in this flow separation zone and squeezes the active width even more. Okay? Now, so over here is the graph that says, well, the larger the diversion angle, the smaller should be the amount of flow that goes in to the abandoned or the channel arm that is being abandoned, and the lower should be the sediment transporting shear stress. Now, as a result of that, if you have a high diversion angle, the sediment transporting shear stress should be small. The sediment that you carry in there will drop out quickly and block off the upstream of the arm. And therefore, little sediment should be transported downstream into the arm to fill up the abandoned channel. Okay? Now, so that was the hypothesis that comes from doing the modeling. Here, whoops, excuse me. Yeah, here are the field data used to try to test that idea. This is the thickness of the gravel deposit at the apex of the abandoned channel. And you see that the thickness, this is 0 to 5 meters, gravel thickness. The gravel thickness at the apex location diminishes again as the diversion angle increases. In other words, out here, there's little, if any, gravel being carried into the abandoned channel and deposited at the apex because the mouth of the abandoned channel is being shut down. Okay? Whereas up here, where the diversion angle is only, say, 20 degrees, the separation zone choking off the channel is small. The flow that goes in there is quite large, establishes enough shear stress to transport sediment all the way, in this case, to the apex of the abandoned channel, and of course, as you saw in the air photographs, all the way down through the abandoned lake. And you can do the same thing, but in this case, just analytically, with a suspended sediment concentration, because again, it's not just a bed material, gravel, that's being transported in there. There's suspended sediment being transported in there, but since the two-dimensional flow model doesn't do a good job of calculating suspended sediment, this is just a calculation of how far, for a given velocity and depth at the inlet, how far along the channel the clay flocks, the silt, and the sand will travel. Okay, so that's our story explaining this difference, that once you form oxbow lakes, as we informally call them, through the chute cutoff process, then you'll develop low diversion angles generally, and the sediment will get into them easily and fill them up quickly. And the opposite will be the case if you have a neck cutoff and a high diversion angle. The sediment will form a blockage right at the mouth here and the mouth there, and the lake will be preserved. Okay, so the third issue that I want to talk about, which is item number 1, is this issue of what if the floodplain is not erodible, all the action comes from bends growing and producing lakes through a neck cutoff process. Okay, now basically we know that the drivers of bend growth the main driver of bend growth is the flow in the channel. And we have a considerable amount of theory about how the flow develops a high shear stress in the pool and the bank on the outside of a bend and undermines the bank, erodes it, and grows the bend. Okay, now circumstantial field evidence, and I'll just illustrate in a minute, suggests that not only the local hydraulics, but the sediment supply generated by the watershed or the mountain range is also a player, if you want to understand how bends grow and produce new channels. So I start out with what I'm calling circumstantial field evidence for this suggestion. I mean, this one is quite well developed by others, but our suggestion is that you better understand the sediment as well. That's particularly relevant if you're going to start establishing new sedimentation regimes in restoration projects and so on. You better have some sense of the response to your alteration of the, or lack of alteration of the sedimentation regime. So the circumstantial evidence for this role, and we try to go through some kind of fluid mechanical analysis to get some kind of scientific underpinning for why that circumstantial evidence arises, and therefore, if we can get to developing a theory of how this works. Now, the current theories based upon of how channels evolved through the fluid dynamics of the flow around the bend was initiated about 30 years ago by this group, and it's been modified since by many others. But at its simplest, what it does is this. It says as the flow goes around the bend, there are 3 sets of forces acting on it to accelerate it, if you like. We have a downstream pressure gradient force, that's the slope of the river, basically. We have the centrifugal force, due to the fact that it's going around the bend. Those 2 forces result in a super elevation, higher water surface elevation on the outside of the bend than the inside. That transverse slope of the water surface creates a transverse pressure gradient which drives, so that's FP, that drives flow, slow-moving flow near the bed towards the inner bank. So the flow, particularly the surface flow, is accelerated towards the outer bank, and there's a countervailing current on the bed, particularly on the downstream side of the bar, that's transporting sediment away from the eroding boundary and building the point bar that then allows the river to move laterally. Now this theory, I'm obviously not going to go into any details on it, and I'm not going to go through this equation, but I just wanted to point out that the essence of this is to say that the rate of bend migration, B, is linearly related to this quantity here, omega I, which is essentially it's the vertically average velocity at the outer bank. Right? And the proportionality between those two velocities is an erodibility coefficient. Erodibility coefficient should then reflect in some way the geotechnical properties of the bank. Is it bedrock? Is it fine-grained sand? Is it cohesive clay? And so on. Now, Candice Constantine and I, and Greg Hansen, tried to evaluate this erodibility coefficient for various bends in the Sacramento River. And then, just to get something real, just not, you get that through calibration. Like, you calculate this, you measure that, plot one against the other, you get an erodibility coefficient. You can imagine all the potential things that might be affected by that erodibility coefficient. But anyway, Candice went out with one of Greg Hansen's jetpack testers that fires a jet of water against an alluvial bank and measures an erodibility coefficient, quite independently of this calculation. And what she showed is that over a range of geotechnical properties of the material, from cemented, weakly cemented gravel through clay to fine-grained sand, sanding gravel, and so on, there's a very strong linear correlation between this calculated erodibility coefficient and something that you can poke your finger in and measure in the field, a geotechnical property. So it enhances the idea that, yeah, this is a pretty good, if approximate, theory, and it makes some sense. But basically what it says is, and this is what reason I put this aesthetic nightmare on here, is it says, well, look, this velocity near the, let's call it the near bank velocity, at location I, where I is any distance around the, any sequence of distances around the bend. This outer bank velocity is a function of the usual kinds of culprits. This is the vertically average velocity, the cross-section average velocity of the river. This is the flow depth. Gravity's in there somewhere, and so on. The normal culprits that would be in any fluid mechanical calculation of flow in a channel. But a couple of interesting features of it is right here, that partial derivative is the curvature, the local rate of change. S is distance downstream. So the rate of change of the orientation, alpha, of the channel at location I, right, where we want the velocity. So curvature is important because of centrifugal force, but also the velocity upstream, like at the preceding calculation cross-section in the numerical calculation. Okay? So the upstream velocity at the outer bank and the curvature are both affecting the velocity near the outer bank at the place we're interested in. Now, if you repeat that calculation, you get omega sub I plus 1, I plus 2, et cetera, et cetera. You repeat that calculation all the way around the bend. Basically what it says is the near bank velocity at any location depends upon the local curvature and the sequence of near bank velocities going upstream to the flow crossing upstream, half a quarter of a meander wavelength back upstream. So the flow is being gradually accelerated outwards as you go around the bend in a manner that reflects the curvature sequence, the sequence of local curvatures as you go around the bend. Okay? So this theory then basically is all about saying it's the curvature and the sequence of curvatures that are important. Okay? Now, this idea was picked up by Stollem way back in, before the break of the millennium there. And he took a simulation code that had been developed on that basis, run by Alan Howard at the University of Virginia. And he said, okay, let me imagine starting out, well, this is the simulation, with a straight line, perturbing it infinitesimally, so I got tiny little bumps of curvature on it, and apply that theory, and predict the sequence of meander bend growth at various times. After a long period of simulation, he comes out with a line like this. Okay? And then he says, well, look, you know, that's like this river channel in the middle of the Amazon basin, the Juruá. Okay? Now, what he said by it looks like, he wasn't just comparing those two traces. He did a spectral analysis on the two, and he showed that, you know, the Fourier sequence of local curvature in the simulation developed with that very simple linear bend theory model ends up looking like the power spectrum of curvatures for the Juruá and the Jandiatuba, I think, and a couple of other rivers. Okay? So the idea was, well, looks good, and also the theory, the simulation, I should say, creates neck cutoffs, so you produce oxbow lakes, and Stollem looked at the frequency distribution of oxbow lakes predicted by the theory, and what he could measure in the Amazon from satellite imagery, and again, looks pretty good. Okay? So the idea is, well, you see, that's how it works. Now, the part that I always was intrigued by is, why did he use for validation of the idea, which is a very exciting one, very interesting one, but why did he have to go to the middle of the Amazon River basin to choose something that looked like the theory? And then I realized that I knew something about these particular rivers in the middle of the Amazon that you couldn't get from the satellite image, because the University of Washington for a while, Jeff Ritchie and a few others of those, would go and measure the sediment loads of these rivers and the main Amazon River. And so what I knew was that these rivers that Stollem had chosen had very low sediment loads. Right? The reason they have very low sediment loads is they're draining the Amazon Craton. This is the Purus here, the Jandiatuba. This is the Juruá. This is Jandiatuba. They don't have, their headwaters are on the very low gradient Craton of Brazil that's thickly still vegetated, and the sediment loads, which we measured, are very low. And in particular, their bed material, the sand that forms the channel margins and the point buds, are very, very low. Where we see lots of rapidly migrating channels are in rivers that head up in the Andes, because they do have large sediment supplies, which again we had measured. So these kinds of, like the pictures I showed you about the third slide in that said, oh, aren't floodplains complex? They're in this sort of area. This is the foreland basin of eastern Bolivia. The topography is like this. The sediment, the rivers come out of the Andes with very high rates of sediment load. The Beni, which is I think this one, which we've surveyed at some considerable length and amusement, has a sediment load of I've forgotten the numbers, but that's typically 200 million tons a year. And by the time it gets to Brazil, it's only carrying 100 million tons. So it's deposited 100 million tons a year in a reach of about 800 kilometers as the crow flies. Okay. And as a result, the river, this is a 40-year record. I'm not sure I can, we have a 40-year record of channel change and oxbow lake formation and channel cutoff and so on. For this river, and we measure migration rates of tens of meters per year. In fact, the reason nobody lives down there is that you can't live anywhere near the river. The river moves around so rapidly it undermines any settlement. Okay? So rapid migration rates are not just driven by local hydrodynamics, but they're also driven by sediment supplies, it looks like. Now that's what I call circumstantial field evidence, which in geomorphology is most of what we have. Okay? Yeah, another example, but I have a number of them, and I'll just give you one other. It's a little closer to home and a little easier to get your head around. This is the Green River in Washington coming out of the western Cascades, the west side of the Cascades. And as it comes out of what's called the Green River Gorge, where its gradient is very steep, it encounters a diminishing gradient across the Puget Sound lowland. Its gradient declines. It starts to drop the coarsest of its sediment and build bars, and as it builds bars, it has to shift to move around them. Okay? So rapid reduction in gradient gives you rapid reduction in transport capacity, gives you rapid increase in deposition rate, gives you rapid increase in shifting rate. And so we have a record of this river going back all the way to the 1890s, or the 1890s or better. 1906 is the best map. So most of that history that I just outlined went on before the era of dam building and diking. So now they've enclosed the lower part of the river successfully in dikes. But the reason that this issue came up was the agencies that were concerned about flood diking and land development in these floodplains said, how come we find it that we're able to control the river shifting in this reach and not in this reach? Right? So here's then a set of data that's getting a little bit, we're still in the circumstantial evidence business here, but here's a graph of distance from the river mouth. So the Green River Canyon coming out of the Cascades is right here at about 70 kilometers. And here's the mouth of the river in Seattle, basically. And the line is a calculation of the total boundary shear stress as an index of transporting capacity. And basically, that means the depth slope product at bankful discharge. That's the index I'm using. And you can see it declines strongly. It's a logarithmic scale. So it's diminishing by a factor of about 10 as the river comes downstream. Then it stays more or less constant for 20 or 30 kilometers. And then it increases at an old tributary of the river that's since been blocked off. But the sediments from the old river are in the bed of the main Green River. And then on the downstream side of that tributary, the transporting capacity again diminishes rapidly as we go down to sea level. Okay? So that's meant to be an indication of transport capacity or even of competence of the river to carry sediment. I have particle size information on the bed of the river, and it obeys the same sort of general pattern. But all of these measurements here are rates of channel shifting over that period, 1906 to 1978. So about 70 years. The different colors are for different periods of time, because one period of time would be stormier than another and so on. So there's a good deal of variability between rates and distances. But if you just look at the black ones for now, which is the oldest data set going back 1906 to I think 1968, you notice that the rates go from about 10 meters per year up there to 3-4 meters per year. And then we have a period where over 70 years there's no measurable shifting. And then there's slight shifting, but only at rates like 1 to several meters per year on the downstream side of that tributary, where again the gradient declines. So again, that's a slightly better controlled circumstantial evidence that when you get sediment in there, and particularly bed material sediment, and it starts to accumulate, it pushes the river around. So then the question is, well, what is there in the theory of flow around bends that would lead you to actually believe that and give you some capacity for quantifying it? Well, what's not in the original theory, and a lot of derivations from it since, is an issue that Jim Smith and Steve McLean pointed out back soon after the theories came out, which is that there's another force. It's somewhat like the centrifugal force. It's looking at the kinematic aspects of the force field. It's not like a dynamical force like the pressure gradient forces. But there's another force due to the shape of the bar on the inside of the bend. And the shape of that bar, particularly the steepness and how convex it is, depends upon the flux of sediment through this cross-section, for example. So Smith and McLean call this the topographic steering force. The argument being then that some aspect of the sedimentology of the channel plays a role in the force field that's not taken account of. So that, to me, is the key to try to make sense out of this circumstantial field evidence, particularly because, of course, if the sediment load is increased, then what the theory suggests is that the bar will become higher and more convex. And also, of course, if sediment is accumulating there, then the bar will continue to grow and progressively increase that topographic steering force and push water out there and increase the shear stress on the outer bank. Now, there's been a fair amount of debate over the succeeding 30 years about the relative magnitude of this force. I would say the majority, until very recently, of theories said, you know, that's a second-order term, we're going to ignore it. But within 2010, there was a laboratory study actually measuring it in a small glass flume with a very sharp bend in it. But there's still a fair amount of concern about whether at real scale, real field scale, that's an important factor in the force balance, and therefore whether sediment conditions, sediment transport supplies, sediment transport rates and sediment supplies could be a significant player in moving that bend around. So I decided, now diverging slightly from my theme of complexity, I decided to try to take advantage of this simple river channel, which was fully reconstructed. Floodplain and river channel over 2.5 kilometers was built by the California state agencies. And this channel, they tried to build a certain amount of realism in it by building typical, for the region again, radius of curvature to width ratios, a slight amount of channel asymmetry, but other than that, things are pretty uniform. So what I'll show you in a minute is I have 10 identical bends, initially identical bends, with a sediment supply coming in from the upper end. And there's a dam upstream, so the flows are controlled, so I have a chance of getting there to make the critical measurements of these forces at a predictable time. And it's not as big as the Amazon, which is much too big for me. It's about 30 meters wide. Okay? So I have a chance of getting some control on this, if you like. The other thing that was a kind of sneaky, intriguing thing that relates back to Wolman is this is a famous diagram from Leopold Wolman's textbook and an earlier paper that they wrote on this subject of river meanders. And what they showed was that whether or not you have a multi-threaded channel or a meandering channel, in some way seems to depend upon the combination of the bankful discharge and the channel slope. And if the slope and the discharge are high enough, then you'll be in this field here above this envelope that they constructed between the the open squares and the closed dots. In this part of the field, you should be braiding, and in that part, you should be meandering. Now, by accident, what these guys actually did was they built this channel right there. Now, I'm not saying that that envelope is known well enough to know which side of that envelope the red X is on, but what it encouraged me to believe maybe was that this river would sometime in my lifetime produce a chute cutoff. Okay? And I could watch it form, define the conditions under which it formed, and test some of these ideas. So in my 10 identical bends, and don't tell me this is not a natural channel. I know it's not a natural channel. You work in the Pacific Northwest and the Amazon, you know natural channels. This is not a natural channel. But it has certain features that are useful to me. It is simple enough to be understood, to be measured. It starts out with these 10 identical bends. It is going to evolve. I get to watch it evolve, hopefully towards normality. Okay? In other words, it will build complexity, but I will be there to document how that came to be, not just that it came to be. Okay? So that's the plan, right? Make high-resolution measurements and high-resolution computations from known initial conditions, measure what happens, keep the fish people involved, and test models at real scale, not in a glass flume. Right? Whether we can test these theories and then generalize the findings to other more unruly, bigger rivers. So we did all that. We go out after the floods and we survey the channel change. So here's the amount of change as a result of 3. Now we've got 4 very well characterized overbank floods should have a recurrence interval of about 5 years. So the bars are growing. What's not so clear from these photographs is the vegetation on the floodplain is actually beginning to look a little bit closer to normal for a Central Valley floodplain. So that's evolving as well. But also, in addition to these bars and the bank erosion that's occurring, this is my developing chute. Right? And it's gradually getting bigger every few years. Now, the reason it's not behaving itself, if you like, at the rate I would like to document is that they made the floodplain out of the same size gravel, 50 millimeter gravel, that's in the channel. Now, in the floodplains of the region, that's not true. This gravel is covered by, in Sacramento, 5 meters of silty sand. So if we had 5 meters of silty sand over here, by now, I think, and at least I calculate, whichever, I think before I calculated, as a matter of fact, but whichever way it was around, that flow should be confined in terms of width over a much more erodible floodplain, and we should have a chute by now. Instead, it's growing slowly because it's still capable of moving this gravel around. And here's what happens this is a 5-year flood again. The main channel flow is going down here. The floodplain is inundated. This is the flow going into the chute. And under those conditions, we can get out there and we can wade across the floodplain with an acoustic Doppler velocimeter, and we can measure the velocities in the floodplain, and we simultaneously get a jet boat out here with an ADCP and measure the velocity field in the channel at 5-year flood, which I don't want to do in those rivers that are coming off the Andes. So simultaneously, we can, not simultaneously, but in the same general time frame, we could get a LiDAR topography of the floodplain, and the LiDAR, of course, allows us to map the vegetation as well, so we can turn vegetation into drag, and we can use that topography and the drag and then the 2-dimensional flow model, and we can calculate, for example, velocity patterns in the channel and the floodplain at various discharges and so on. And we can validate those measurements against our field, validate those calculations against our field measurements. Right? That's what we're trying to do. So then we can query the model predictions with some more confidence to say, yeah, these are the unmeasurable terms in the force balance are represented in the model here, this way. And we know that the representation is good because we validated the flow model against velocity beta measurements. As a result, by the way, this is just an output from the most recent flood, and you see that it does have high velocity, the model now has high velocity water coming over bank just where Jose Constantine wants it, and it's beginning to erode that chute that I talked to you about. So this is, if you like, a Constantine chute. Now, the other thing that emerged from this modeling that doesn't seem to occur in the Sacramento, but I've noticed on satellite images in tropical floodplains, is that there's another tendency for high velocity water, not as high as this velocity, but for high velocity water to short circuit the bend here in this location B and produce another chute channel. And under certain circumstances, which I'm not prepared to generalize about right now, but they're some combination of fine-grained sediment, sandy rivers, and sediment-starved conditions, where this gradient, transverse gradient across here tends to be low, that flow should go over bank there and produce another type of chute. Okay, so here's examples. This is, our ADCP, and we can get 3-dimensional velocity fields from it. It allows us to calculate streamwise cross-section and vertical velocities. We can use those measurements then to validate that our 2-dimensional flow model is giving us about the right values here. And then we can use the flow model then to give us this other simulation of flow fields in 3 dimensions in various floods. Okay? Now, again, the reason for doing that is so that then we'll have more confidence in the fluid mechanical modeling. But just let me say, before we do that, another thing we can also do is we can use the fluid dynamical modeling to calculate what this value tau here, the blue dots, what the velocity and the shear stress should be in that critical outer bank. And we can measure the rate at which the bank goes back during the flood. Okay? So we can test the linear relationship between that velocity and a slightly modified version of that velocity and the bank erosion rate. Now, it's not quite as simple as the initial proposal that B equals E times omega, but it does look to a satisfying degree for field data that the erosion rate, in this case, this is not erodibility, but erosion rate, is a linear function of the excess shear stress. In other words, the predicted or calculated shear stress on the bank minus the critical shear stress for that material. So that there is some relationship between outer bank shear stress and bank migration rate. So, but going back to the theoretical underpinning for the circumstantial evidence that sediment ought to have an influence on this process, we wanted to determine whether that topographic steering force was an important player in the force balance, right? And therefore whether you should expect sediment to have a relationship. So now we can go into that validated flow model, back calculate out the force components in downstream and cross-stream directions, and I'm not going to go through this, but just to point out that they are identifiable. You can calculate them from the output of the model once you can find it, and you can map. For example, this is one component, the computed cross-stream convective acceleration due to the topographic steering, and how that evolves over time as we go from the initial form of the channel to after 3 floods, 2 big ones and a small one. The bar has grown, and you see more warm colors in here, meaning there's more of that particular cross-stream force component in the flow. So the bar is pushing the water outwards. If we add up the 2 cross-stream flow components, I haven't done it here, but if we add them up, it turns out that that the answer to the debate, at least for this river, is that in a real river, the topographic steering force is at least the magnitude of the curvature force. Okay? So yes, bar form controlled by sediment supply ought to have an influence on the outer bank discharge. And so we can model how the shear stress field grows as the bar grows. Now, the next thing we are trying to do then is to say, okay, well, now let's try to grow a bar by modeling. Let's not only flow down the channel, but let's give it a sediment supply and see if we can build the bar, increase the shear stress on the outer bank, use our empirical bank erosion rate equation, and predict not only bar growing, but bank migration. Not only the rate, but the pattern, and the differential rate of bank migration around the bend changes the shape of the bend and alters the form of the meander. Okay? Now, we're working on that. It turns out it's hard to do because it's very hard to stabilize these high-resolution numerical flow and sediment transport models. So they run for a couple of years and then they go crazy because there's some tiny little curvature in the discretization, and so you can't get them to run for 30 years or whatever. And also, we've only tried the sediment transport formula that's built into FastMech, the Geological Survey's 2D flow and sediment transport model. So, you know, we're not there yet. But what the strategy is to try to do this. This is the initial condition at 3 different, the black line is the initial condition at 3 different cross sections. The blue dashed line is our surveyed measurements of the topographic change over 3 floods, and the red is the prediction of the bed evolution change. Now, whether you shouldn't expect any, we don't get any. Where you should expect some change, we kind of get the magnitude about right, but we don't have it completely filled in yet. Whether that's just a time problem. If we could run the model for longer, it would fill in this gap, but that's the part we're still working on. Okay? So as a result, I got a little bit impatient to push this argument further along, and so I tried to explore it one step further with a simpler flow and sediment transport model, and apply it back to the old Sacramento River. And the question I'm asking is the ability of the river to drop sediment in certain reaches and therefore drive the flow outwards to accelerate the erosion on this bank, is that an important player? Or as I translated that into researchable terms, is there a relationship between the rate of sediment supply and the rate of bank erosion, all other things being equal? And if so, what's changing? What is it that drives that bank faster? So we have a nice DEM of the channel and the floodplain of the Sacramento, so I cut a piece of that out. By this time, all my graduate students have gone away, so everything slows down because I have to do this myself. So you see a lot of string and sealing wax in this calculation. But anyway, we cut cross sections out of it, and we ran Fluvial 12, which is it's called a one-dimensional flow, sediment, and bed evolution model that Howard Chang developed. The value of it over things like HEC-RAS, that some of you may be familiar with, is it allows the river to be to go around bends. In other words, it allows curvature in the model, and it allows bank erodibility to be modeled, and it transports sediment. And Howard put a gravel sediment transporting model that Mike Singer and I cobbled together into it for us. So that's the reason we're using Fluvial 12, for those of you who would ask why we did that. But I started out with this, a single bend of Sacramento River topography. I established bank full discharge, put the particle sizes that we'd measured on the bed. I put a constant rate of sediment input, various sediment input rates at the upper end. I calculated the bed load transport and the deposition and the bank erosion and channel change, and I simulated decades of sediment transport and channel change. Okay, now again, I know that we don't get bank full discharge at a constant rate for 30 years in a real river, but this is an illustration of the principle. Now, basically, cut a long story short, the kind of result we get, if I set the bank erodibility at a fixed value, similar to what Candace Constantine had evaluated for the real Sacramento River, and I alter the sediment supply systematically, and I run the model for 30 years, then what happens is it builds bars, it drives the channel laterally. These are predicted cross sections, and I measure the bank erosion rate by the retreat rate of that outer bank. For example, if I double the sediment supply rate, all other things being equal, I increase the bank erosion rate. Not quite by a factor of 2, but sediment supply does have an influence. If I do a systematic set of simulations and I alter the sediment supply systematically, I won't go into details of this scale, but it's basically I established a steady state sediment transport rate that I call the reference sediment supply rate, and I take fractions of that from 0 to 1.5 times. And I alter the erodibility, that's these different colors, and the bank migration rate responds in that way. And as it does so, why is it doing so? Because the near bank velocity also depends on the sediment supply rate for different erodibilities. Okay? So now the thing I'd like to do next, but this is the slowing down part because of the age scale of the research assistant significantly increased. There's nothing in Fluvial 12 that allows the river to shift over and continuously modify itself. And of course, as the bank erosion, this is just a sketch now. The red is the initial condition, but differential rates of bank erosion around the bend are going to change the curvature of the bend. And since curvature is in the driver in the model, then as the curvature changes, it's going to feed back on the sediment transport rate. So I'm still trying to figure out a way of making Fluvial 12 do that, but it requires, my GIS skills are slowly improving, but I'll get there. But my summary basically of the whole talk is then, we have some ideas about how new channels get produced by chute cutoff, and these are the variables that seem to be dominant. in explaining differences between different places in the occurrence of these chutes. And there's another chute forming across the point bar. I have beginnings of a hypothesis about why. We'll explore that, but the answer's to be determined. On the second of the issues, the rate patterns of sediment transport, rates of sediment transport into oxbow lakes, and the filling of the oxbow lake depends upon these two sets of factors. The bend growth for, when all the action's inside the channel, there's obviously a strong internal effect due to the fluid mechanics. The flow is going around the bend, and the outer velocity is, outer near bank velocity is driven by the curvature series as you go around the bend. But also, to some extent, by the topography, the shape of the bar, and the bar shape, how convex and high it is, depends upon the sediment supply, and also the fact that the sediment supply is, in some places, causing accumulation and growth of the bar. Both those two effects give you a sediment supply effect on bend growth and channel migration. And that means, of course, that the watershed is playing a big role on it, and watershed, mountain range, whatever you want to call it. So, what I've called here the meta-summary of the summaries is that the origin of these complex features are reducible of floodplains are reducible for analysis and maybe prediction through some combination of fluid mechanical modeling and field investigation. And there is a good Wolman centered reason for doing it, because these aspects are killing people, and we need to know more about them. And we also need to use some of these concepts if we want to predict the future of these newly restored channels and floodplains that we're investigating or investing in. That's all I have to say. Thank you.
Great talk. We started a bit late today, but we would still want to take some questions. So if you're going to turn this on, I'd like to use this everyone. So let's take some questions. We should push our break back a little bit, but let's push our sessions back. Maybe we start our sessions at 10:20. So let's take time to have some questions. All right. Let's see. How about now?
Tom, going back to your theme of complexity, we know that some people have tried to quantify this complexity through nonlinear dynamics, and specifically Stolum, in the study that you mentioned. Using the Howard model, he claimed chaotic behavior. In a sense, basically, the emergence of cutoffs in short periods of time, kind of a memory through the system. Do you have any physical insight in that?
Into Stolum's predictions? Well, I mean, yes, I think that what he was simulating and what he predicted is the conditions where the floodplain is not erodible, and all the erosion occurs but through in-channel bank erosion, that therefore builds very sinuous channels and oxbow lake neck cutoffs, because when the water goes over bank, it's not competent to erode new channels that would cut the bend off and short circuit the process. So in fact, what we're trying to do is redo Stolum for the chute cutoff part of the world, right? For these erodible floodplain circumstances. The only thing that I didn't think was defensible in what Stolum did is he cut, once he had a power graph, he immediately jumps to saying, oh, well, must be self-organized criticality. And then from then on, all the talk is self-organized criticality. And self-organized criticality leads to complexity and so on. I'm 30 years behind here saying, wait a minute, guys. What about, I don't even know how self-organized criticality should work for this process. So let me go back and reduce the complexity of my approach. This is all about fluid forces and sediment interactions, and I will try to explain to you why Stolum got his results and validated them in the middle of the Amazon craton only, whereas if I try it out some other place, I don't necessarily get the same power law. I don't get a straight line anyway. So there's nothing wrong with, I think that stolen paper is a very interesting and stimulating paper. It's the suspending all physical insight and leaping to a log plot that bothers me. I mean, well, not say bothers me, it just doesn't interest me.
But just basically doing the micro-scale analysis and try to understand in the pattern dynamics what might be a little more organization that arise from the micro-scale processes that we talk about. That's very interesting. And under what conditions? Bank erosion or sediment accumulation?
Yeah. So well, my message was that under those circumstances, very low sediment supply and non-erodible floodplains, this very simple proposal that comes out of the perturbation analysis that Ikeda Parker went through gives you that complexity. I mean, I think that's a really nice result, and I'm somewhat surprised that it hasn't been followed up by people. Alan Howard has probably followed it up most in terms of simulating patterns, also in the 90s. In fact, it's Alan's program that Stollum used. But it seems to me there's a lot more richness in the problem, if you like.
Thanks for a great talk. You concentrated, especially for the chutes, at the point the flow and the sediment exits the meander itself. Now, one potential outcome that we know is that you're simply going to get a downstream migration of the meander because the area of chief curvature is migrating downstream as well. In addition to concentrating on the point where the flow exits, how about where the flow re-enters the stream itself? So one thing in your constructed channel, besides having very coarse-grained floodplain material, they probably leveled the entire floodplain itself. I'm just looking at a Google Earth site at a river I was on in Ecuador 2 weeks ago, and I was interested in all these cuts or small tributaries that enter the river, but they have no upstream drainage area. So they're activated when the water is actually emerging that flows up the river and from other areas, and then re-enters, and because you have this curvature and convergence, and presumably you've dropped a good deal of your sediment load further on. This might be also in the low sediment areas why this might work. What's the role of what's happening as you re-enter the river and that pre-flood topography of the floodplain itself?
Yeah, unfortunately, the reason I abandoned trying to make sense out of those kinds of rivers in the Amazon basin is that they're so complex, and the history of channel change locally is determining a lot of what's happening. Not just the cutoff itself, but lots of other things happen. And so I don't have a simple, straightforward answer for that. But I will say, I think, again, I haven't seen this in Ecuador, but in the Fallen Basin of Bolivia and in the main Amazon down in Brazil, a lot of very local runoff, because the wettest part of the Amazon basin is in the lowlands. It's not in the mountains. So there's 3 meters to 5 meters of local runoff occurring, with coming off and feeding into the floodplain and carrying no sediment. And I think a lot of those channels, that at least the most recent implementation of them, if you like, that we see now, are because of localized runoff. And the annual draining of the lake, because again, in the main stem of the Amazon, the stage changes by 10 meters, so it fills up 10 meters of lake, and the channel, the water goes down, and all that drains out again through the downstream end of these lakes. Now, the place where there's been the strongest proposal for an upstream migrating channel, I think have been in this country. But they've been in places where some kind of blockage, either an ice jam or a log jam, on the downstream end of the meander backs up the water, backs up all the way around to where the water's coming out, and it drops the water surface down below the jam. So when the water comes out of this bend upstream and goes across the floodplain, and it gets back in the channel, it's going down a riverbank. Okay? Now in a natural channel that's not blocked, the water down there is just as high, it's up above the riverbank, or at the riverbank, when the water's going over bank here. So there's no strong local slope to initiate one of those retreating channels, right, that would then short circuit the bend. So I think that upstream migrating or downstream initiated chutes can form, but the circumstances where I think I understand them the best is where the channel is small enough to be blocked and to have a step in the water surface profile.
Okay, let's, I'm going to encourage one-part questions at the moment. So we're going to move, we'll take a question from Gordon, and then VTech, and then we'll move for a break, and once again, one part, no follow-ups.
Actually, Tom, I think you just answered the question I had, which is this idea that, can I mean, the mechanism you invoke for erosion is a top-down sort of shear stress limited mechanism, but if you do have any sort of declivity that allows a channel to work its way back up, and I've seen that. I've actually seen you know, erosion that unzips underneath the vegetation. So the vegetation was actually cantilevered out because of this sort of rotary effect. But it may be just an anomalous, unusual thing where you get a blockage or some sort of steep relation.
I mean, that's my story for now, because it's the only thing I can provide any kind of, contribute any kind of suggestion about the fluid mechanics of it. I'm not saying that it never happens.
So what are the lessons learned from this research for FEMA-like flood inundation, you know, maps required by regulatory agencies?
Well, I mean, I haven't spent a lot of time thinking about that because I don't encounter FEMA much anymore. But I would say there are things like, if you are trying to predict the future of a river, you better have a good handle on the sediment supply, which is a hard thing to do, and why we typically don't do it. The sediment supply, you know, if you write a paper on a river, when you're describing the field area, you better tell me the bankful discharge and the gradient, because everybody agrees those are fundamental controls. I would say you better do those two things and the sediment supply, because that's just as fundamental. Right? So I think that's one thing. Another one is that it is apparently possible to do a pretty good job on predicting bend migration and the conditions under which you might expect new channels to form. And if new channels have formed and you're an ecologist, not FEMA, predicting the future, succession, both aquatic and terrestrial in that terrain, in that lake, is also doable. And then I think the other thing is it helps to, and this now goes back to the Bangkok issue, where we have a lot of these floodplains that have these very subtle features on them, the significance of which is not fully appreciated by the people who are trying to decide where to build. And I mean the agencies, not just individual entrepreneurs. So it sets, puts our eye in to the conditions where complexities in the inundation are likely to happen, and complexities in the topography are likely to evolve. And so there's the things that come off the top of my head.
Okay, let's thank Tom once again for a great talk. And again, we're pushed back a little bit. Let's take our break now, and let's begin the sessions at 10:30. I keep the same time, and it'll push the lunch back, but we have the free afternoon. I assume that's okay with the organizers. Which is where again? Oh, it's in this program.